Welcome to the lecture on dynamic programming module 2. In this module, we will discuss dynamic programming model 3, which considers single multiplicative constraint and additively separable return function. We will also discuss the solution of discrete dynamic programming problems and solution of linear programming problem by dynamic programming algorithm or dynamic programming technique. Let us now proceed to discuss dynamic programming model 3. This model considers single multiplicative constraint and additively separable return function. We consider the problem minimize z equal to f1 y1 plus f2 y2 plus dot 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 fn yn subject to the constraint y1 y2 up to yn is greater than or equal to p, where p is greater than or equal to 0 and yj is greater than or equal to 0 for all j. We define the state variables as follows: Sn is equal to y1, Sn is equal to yn minus 1 dot 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 y2 into y1, which is greater than or equal to p. Sn minus 1 is equal to Sn by yn, which is equal to yn minus 1 yn minus 2 dot 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 y2 into y1. And similarly, we get S2 equal to S3 by y3, which is equal to y2 into y1, and finally, S1 equal to S2 by y2, which is equal to y1. These state variables are stage transformation of the type Sj minus 1 equal to Tj into Sjyj. Let capital F Sn be the minimum value of the objective function for any feasible Sn. Then proceeding similarly as earlier, we can obtain the recursive formula as capital Fj Sj equal to minimum of Fj Yj plus capital Fj minus 1 Sj minus 1, and the minimum is taken over Yj. We now consider an example. Use Bellman's principle of optimality to minimize z equal to y1 plus y2 plus dot 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 plus yn subject to y1 into y2 dot 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 into yn, which is equal to d, where yj is greater than or equal to 0 for all j equal to 1 to up to n. Let f and d denote the minimum attainable sum of yn plus y2 plus y3 plus dot 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 yn when the quantity d is factorized into n factors. For n equal to 1, d is factorized into one factor only. So, f1 d is equal to minimum of y1, which is equal to d. For n equal to 2, d is factorized into two factors y1 and y2. So, if you assume y1 equal to x and y2 equal to d by x, then f2 d equal to minimum of y1 plus y2, which is equal to minimum of x plus d by x, where 0 less than x less than equal to d, and this can be written as minimum of x plus f1 d by x, since f1 d by x equal to d by x. Now, for n equal to 3, d is factorized into three factors, where y1, y2, y3 are those three factors, and if we assume y1 equal to x, then obviously y2, y3 will be equal to d by x. Then f3 d is equal to minimum of y1 plus y2 plus y3, which is equal to minimum of x plus f2 d by x, where 0 less than x less than equal to d. Proceeding likewise, the recurrence relation for n equal to y can be obtained as f I d equal to minimum of x plus f I minus 1 d by x, where 0 less than x less than equal to d. Now, we proceed to solve this function equation. We have f 1 d equal to d and f 2 d equal to minimum of x plus d by x, which can be obtained as root d plus d by root d. Since the minimum can be obtained for x equal to root d, therefore, we get f 2 d equal to 2 root d. Similarly, f 3 d is equal to minimum of x plus f 2 d by x, which is equal to minimum of x plus 2 root over d by x, and then we find the value of x, which minimizes x plus 2 root over d by x, and finally, we get the value of f 3 d as 3 d to the power 1/3. By induction hypothesis for n equal to m, we get f m d is equal to m d to the power 1 by m. Now, this result can be proved for n equal to m plus 1 as follows. We have f m plus 1 d equal to minimum of x plus f m d by x, and which is equal to m plus 1 into d to the power 1 by m plus 1. Hence, the optimal policy is obtained as d to the power 1 by n, d to the power 1 by n dot 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 d to the power 1 by n, with f n d equal to n d to the power 1 by n. Now, we proceed to find solution of discrete dynamic programming problem. We will find the solution of discrete dynamic programming problem for taking practical examples. Suppose that the owner of a chain of 4 grocery stores has purchased 6 crates of fresh strawberries. The estimated probability distribution of potential sales of the strawberries before spoilage differ among the 4 stores. The following table gives the estimated total expected profit at each store when it is allocated various numbers of crates. This table shows that there are 4 stores 1, 2, 3, 4, and available crates is 6, that is the number of boxes is 6, and when we allocate 0 box to store 1, the expected profit is 0, and similarly 0 box to store 2, 3 and 4, we have the profit 0. And if we allocate 1 box to store 1, the profit is 4, 1 box to store 2, profit is 2, 1 box to store 3, profit is 6, and 1 box to store 4, profit is 2. Similarly, for allocation of 2, 3, 4, 5, 6 boxes to different stores are shown in this table. For administrative reasons, the owner does not wish to split crates between stores. However, he is willing to distribute 0 crates to any of his stores. We have to find the allocation of 6 crates to the stores so as to maximize the expected profit. Let the 4 stores be considered as 4 stages in a dynamic programming formulation. The decision variables x j denote the number of crates allocated at the jth stage. Let P j x j be the expected profit from allocation of x j crates to store j. Then the problem can be formulated as an LPP, maximize z equal to P1 x1 plus P2 x2 plus P3 x3 plus P4 x4, and obviously the constraint x1 plus x2 plus x3 plus x4 must be equal to 6, which is the total number of crates. Let x j be the allocation at stage j and s be the number of crates still available at this stage. We define f j x j as the value of the optimal allocation for stores 1 to 4. If f j s x j be the profit associated with the optimum solution f j star s, then f 4 star s equal to maximum of f 4 s x 4, where x 4 takes values between 0 and s, and which is nothing but maximum of P 4 x 4. Then the recurrence relation can be obtained for j equal to 1, 2 and 3 as f j s x j equal to P j x j plus f j plus 1 star s minus x j. The solution to this problem starts with f 4 star s, that is, we will first allocate in the fourth store and then we will proceed backward. The computations for the first stage, that is allocating at store j, is as follows. The available crates are 0, 1, 2, 3, 4, 5 and 6, and the units which we can allocate to store 4 for when the available crates is 0 and we allocate to the store 4 as 0, the profit is 0. From the table we can get these values. When the available crates is 1 and we allocate to the store 4 1 crates, then the profit is 2. Similarly, we can find the other values. See that when the available crates is 4, we have the maximum profit is 4. So, we can allocate in the fourth store 3 or 4. If we allocate 3 boxes, then we get the profit 4. It shows in the previous row, and even if we allocate 4 boxes in store 4, then also we get the profit 4. So, similarly for s equal to 5 and 6, we can calculate s 4 star s, the optimal profit. Now, this is the computation for stage 1. Now, we proceed to stage 2. We have the recurrence relation f 3 is equal to P 3 x 3 plus f 4 star s minus x 3. F 4 star we have already derived in the previous table. So, depending on the available value of s, we can take or we can assume the value of x 3. For instance, in the first row availability is 0 So, we can x 3 can take value 0 only, and when x 3 equal to 0, we can find the value of f 3 which is equal to p 3 0 plus f 4 star s minus 0. Similarly, we can calculate the values for s equal to 1, 2, 3, 4, 5 and 6, and the optimal value of x 3 star also given. Now, proceeding similarly, we can find the results for stage 3 as shown in this slide, and finally, in the fourth stage, since there is no other stage left, so we have to allocate the total number of available states which is 6. So, S will take the value 6 only, and then from the reconciliation we can find the values of f 1 star for different values of x 1 as shown in this table. So, from this table we see that the optimal value of the profit is 18, and this is obtained for values of x 1 can take the value 1 and 2. When x 1 can take the value 1, we have the remaining or available value of s is 4 minus 1, that is equal to 3, and if x 1 takes the value 2, then we have the available crates is equal to 2, and that we can get the optimal value from the previous table. So, from the above computation, it is observed that the maximum profit is rupees 18, and that can be obtained by choosing the following 8 alternative solutions. You see that the x 1 can take values 1 and 2, as I already mentioned from the last table, and depending on these values we find the values of x 2, x 3 and x 4 going backward and following the results of the table shown already. Now, we proceed to take another example which is called cargo load problem. A vessel is to be loaded with stocks of 3 items. Each unit of item I has a weight Wi and value Ri. The maximum cargo weight the vessel can take is 5, and the details of the 3 items are as follows. We have the item 1, 2, 3, weight item 1, weight of item 1, 2 and 3 are 1, 3 and 2 respectively, and the value of the items are 30, 80 and 65 respectively. Develop the recursive equation for the above case and find the most valuable cargo load without exceeding the maximum cargo weight by using dynamic programming. Here we have to determine how many units of 3 items, item 1, 2 and 3 to be loaded. So, it is a 3-stage problem, and we assume x j as the number of units to be loaded at stage j, and s be the number of units still to load at this stage. Let f j x j denote the value of the optimal allocation for the 3 types of items, and if f j s x j be the value associated with the optimum solution f j star s, then we have the recursive equation. F 1 star is equal to maximum of f1 s x1, where x1 takes the value between 0 and s, 0 less than x1 less than equal to s, and fj star is equal to maximum of pj xj plus fj minus 1 s minus xj for j equal to 2 and 3. Here pj xj denote the expected value obtained from allocation of xj units of weight to the item j. Now, for one stage problem, we have f1 star equal to maximum of 30 x1, where largest value of x1 is 5. We have the following tabular computations. S can take the value 0, 1, 2, 3, 4, 5, and x1 also can take the value 0, 1, 2, 3, 4 and 5. Therefore, depending on these values of s and x1, we can find the value of 30 x1 as shown in this slide, and from this we find the optimum value of f1 for each row, and similarly we can find the optimum value of x1 star. For two stage problem, the largest value of x2 is equal to 1, and we use the recurrence relation f2 star equal to a maximum of 80 x2 plus f1 into s minus 3 x2, and here s also can take the values 0, 1, 2, 3, 4 and 5, but x2 can take value 0 and 1 only. So, we calculate the values of 80 x2 plus f1 star s minus 3 x2 for different values of x2 and s, and corresponding f2 star s and x2 star as shown in this slide. Proceeding similarly, we find the values for 3 stage problem as shown in this slide, and from these results we see that the optimum solution is x3 equal to 2, which is obtained from the last table. From the last row, we see that x3 takes the value 2 and giving the maximum value 160. So, when x3 takes 2, so we have the remaining value of s is equal to 1, and from the previous table we see that when the value s takes 1, we have x2 star equal to 0, and when x2 star equal to 0, then from the previous table, that is from table 1, we find x1 star equal to 1. Thus, we find the optimal solution as x3 star equal to 2, x2 star equal to 0, x1 star equal to 1, with the maximum value of load equal to 160. We were discussing how to find the solution of discrete dynamic programming problems. Here we have taken two examples, product allocation problem and cargo load problem. We will now proceed to see how an LPP can be solved by using dynamic programming technique. Consider the general linear programming problem. Maximize z is equal to c1 x1 plus c2 x2 plus dot 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 plus cn xn, subject to a I1 x1 plus a I2 x2 plus dot 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 plus a in xn is less than equal to bi, where I equal to 1 to up to m, and x j is greater than equal to 0 for all j equal to 1 to up to n. This problem can be formulated as a dynamic programming problem as follows. Let the general LPP 1 be considered as a multi-stage problem with each activity j as individual stage. Then this is an n stage problem and the decision variables are the levels of activities x j at stage j. As x j is continuous, each activity has an infinite number of alternatives within the feasible region. Here each constraint represents the limitation of different resources. Therefore, the state must be represented by an m component vector which is b 1 b 2 dot 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 b m. Let f n b 1 b 2 b m be the maximum value of the general LPP defined above for stages x 1 x 2 up to x m for states b 1 b 2 up to b m. Now, using forward computational procedure, the recursive equation can be obtained as f j b 1 b 2 up to b m is equal to maximum of c j x j plus f j minus 1 b 1 minus a 1 j x j b 2 minus a 2 j x j dot 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 b m minus a m j x j, where 0 less than equal to x j less than equal to b. The maximum value of b that x j can assume is minimum of b 1 by a 1 j, b 2 by a 2 j dot 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 b m by a m j. Here we consider the minimum value because it satisfies the set of constraints simultaneously. Let us take an example. Maximize z equal to 3 x 1 plus 5 x 2 subject to x 1 less than equal to 4, x 2 less than equal to 6, 3 x 1 plus 2 x 2 is less than equal to 18, x 1 x 2 greater than equal to 0. In this problem, we have two variables x 1 and x 2. So, the problem can be considered as a two stage dynamic programming problem. The states of the equivalent dynamic programming problem will be b 1 equal to 4, b 2 equal to 6 and b 3 equal to 18. Therefore, for the first stage we have f 1 b 1 b 2 b 3 equal to maximum of 3 x 1. So, we will consider only for x 1 in the objective function, not x 2. So, we will consider maximum of 3 x 1, where 0 less than equal to x 1 less than equal to b, and the maximum value of b that x 1 can assume is minimum of 4 by 1, 6 by 0 and 18 by 3, which is equal to 4. Therefore, f 1 4, 6, 18 is equal to maximum of 3 x 1. Since x 1 is less than equal to 4 from the first constraint and from the third constraint x 1 is less than equal to 18 minus 2 x 2 by 3. Therefore, we have to consider the minimum of these two. Hence, we write 3 into minimum of 4, 18 minus 2 x 2 by 3. For the two stage problem, we have f 2 b 1 b 2 b 3 equal to maximum of 5 x 2 plus 3 x 1, where the maximum value of b that x 2 can assume is minimum of 4 by 0, 6 by 1 and 18 by 2, which gives 6. Therefore, f 2 4 6 18 equal to maximum of 5 x 2 plus, we put the value of x 1 here, that is minimum of 3 into minimum of 4 18 minus 2 x 2 by 3. Now, minimum of 4 18 minus 2 x 2 by 3 is equal to 4 if 0 less than equal to x 2 less than equal to 3, and it is equal to 18 minus 2 x 2 by 3 if 3 less than x 2 less than equal to 6. Therefore, 5 x 2 plus 3 minimum of 4 18 minus 2 x 2 by 3 will be equal to 5 x 2 plus 12 if 0 less than equal to x 2 less than equal to 3, and it is equal to 18 plus 3 x 2 if 3 less than x 2 less than equal to 6. And from this we see that the maximum value of 5 x 2 plus 12 is 27 at x 2 equal to 3, and the maximum value of 18 plus 3 x 2 is 36, which occurs at x 2 equal to 6. Thus, the optimum value of f 2 4 6 18 will be 36 for x 2 equal to 6. Hence, the optimum solution is max z equal to 36 with x 2 star equal to 6 and x 1 star equal to minimum of 4 18 minus 2 x 2 by 3. If we put the value of x 2 here, we find the minimum as 2. So, x 1 star equal to 2. In this module, we have discussed dynamic programming model 3. We have also learned how to find solution of discrete dynamic programming problem by using tabular computation, and we have also discussed how to find solution of linear programming problem by using dynamic programming technique. With this comment, we end this module as well as this chapter.